All right, guys, we are going to hopefully finish up the section on astrophysics today. There will not be vocabulary or reaction paper due over this section. So you're done for the year if you have that.
I could not open the link.
Okay, so if you're unable to view a PowerPoint from Cartwright, it is probably because I made PowerPoint using a program called LibreOffice instead of Microsoft Word.
Yes.
I had about a 30-minute ordeal over that.
Sorry about that.
I checked it at like 9 a.m. last night. And I was like,
So you might want to download LibreOffice. It's a free download. It doesn't take up very much space on your computer, and it will open any Word document ever. So that's kind of nice. However, Word doesn't like it. So if you try to open a LibreOffice document with Word, it's out of the question. Yeah, please don't email it to me. Just bring it next week. Okay. Because I get enough homework emailed to me, and I've been known to occasionally, if you get 200 or 300 emails a week, it just stuff gets lost in the chaos of that. So, all right. So we're going to get into some astrophysics here, and this is again just FYI. I'm not going to require any work over here. This is the time of the year where most of the government schools are switching over to their testing regimen. So this is just like gravy. Like we don't do that because like why would you? So we talked about experts in the field that were convinced that there was no blind forces here. Okay. That God does not play dice with the universe, and of course that there is an order and laws that govern this universe, and they make a mockery of any attempt to explain the universe without God. All right, we talked about the fact the Big Bang is a lot more in line with a young Earth creation worldview than an atheistic worldview, because it is a linear view of the universe. The universe had a beginning, it will have an end. They just can't keep going on forever. This is in contrast to the other two options, right? There's two other options for the existence of the universe. One being that the universe is eternal. It always has been and always will be. That was actually Einstein's model, right? He believed the universe was eternal. He was a steady state guy. That is why he had such a problem with black holes. I couldn't figure out why Einstein predicted black holes in his theory of relativity and still didn't like them. And I finally figured out it's because black holes mean the universe cannot possibly be eternal. Once matter gets sucked into a black hole, you're not getting it back. It's gone forever. Okay. So Einstein was like, well, there's got to be like a white hole out there somewhere that's spewing matter out into the universe and replenishing the amount of matter and energy that black holes consume, which is of course impossible. Okay. So
Teleportation.
Yeah. Let's just break physics a little bit.
Just a little bit.
Well, you can't break those laws. That's out of the question. So there's either the steady state, having that has all happened before, all happened again, or it's a cyclical nature of the universe. This is what the Hindus believe, right? That you have these cycles in nature, and everything just kind of goes through cycles. Both of those are impossible according to science. So it turns out a linear view of the universe is the correct one. And how is it possible that the Christians and Jews have had this right for thousands of years? Well, maybe somebody told them that the universe has a linear nature to it. Okay, we talked about the fact that the Big Bang is not really much of a scientific theory, and that the experts at the time were not super happy about it, right? When the scientific community got dragged kicking and screaming into the Big Bang in the 1980s, they basically said, okay, we'll tolerate this for a while, but we are not happy about it, and basically we want a new theory within 10 years, and we're just going to tolerate this for a little while, because we're going back to the steady state. This Big Bang is way too much like the theory of, actually, I think it was Fred Hoyle, I meant somebody else, said the Big Bang is the theory of sudden creation. They were not okay with that. Basically, you're saying 1 minute there was nothing, and the next minute, boom, everything. That sounds a lot like Genesis. We're not okay with this. So what pushed him into such a vulnerable worldview? Well, good question. Okay. One thing that sort of dragged him into this was the fact that the universe has expanded. All right. Now, we don't know if it's still expanding. I want to point this out. A lot of people think that it is, and they're just convinced that that's the case. Quite impossible. Okay. We used to think redshift was a byproduct of the universe expanding. It cannot be, because if the universe is expanding that fast, we have now discovered that quasars would have to be moving away from us at like 90% the speed of light. That much speed would actually destroy the structure of galaxies. Okay, so it's quite impossible for them to be moving away from us.
And so then we thought, well, maybe space itself is expanding. This is logically impossible. Remember we talked about this last week? Okay, so why can space not be expanding?
Where would it expand?
Exactly. Space has zero pressure. If it's expanding into something, it would have to have negative pressure that it's expanding in. This is not a thing. Okay.
Past space is nothing.
Or, you couldn't describe it scientifically.
Yeah.
It's beyond the reach of science, right? We talk about like all
Physically,
year,
nothing.
right? Or maybe that's where heaven is, or I'm not really sure. So redshift is not due to a velocity, and it is not due to the expansion of space-time. And you might ask yourself, well, what in the name of logic and reason is going on with all this redshift? Excellent question. We have also discovered that redshift is not a smooth, steady increase as you get out into the cosmos. We developed a formula for it, because if it's an exponential function, it should fit some formula in math, right? And so we have our little formula about redshift, and redshift is supposed to do something like that. As you get further and further away from the Milky Way, redshift increases faster and faster till you get out to the quasars, where redshift is going nuts on you. However, a couple of problems. First of all, the formula we have for redshift only works in the first 7/8 of the universe. When you get out to the cosmos, the formula changes, which again indicates that it's not due to an expansion, right? So something weird is going on there. We've also discovered something which you guys may remember from the video with Barry Setterfield, which I know is extraordinarily technical. We've discovered that redshift is quantized, okay? Meaning that it does not follow this nice smooth little line as you get out into the cosmos, but rather increases stepwise. So in other words, a certain distance from the Earth, you have a certain redshift, which is the same as ours. It just looks like normal light. And then when you get a certain distance away, it all jumps up to another value. And you get a little bit further away, and it's another value. And you get a little bit further away, and it's another value. And it's kind of going stepwise like this. Okay. Why is redshift quantized? Well, scientists don't know. Now I say that it's not because I understand the math that's involved. I have studied redshift. The math is far beyond my ability to understand. Okay, so know that. We're talking about 6 or 7 years of post-calculus math to be able to do this kind of stuff. Okay, so if you want to be an astronomer, you're going to have to like some math. Okay. Or not. Some astronomers know nothing about math, and all they do all day is look at photographic plates. So that's also kind of like being in biology. You can do population studies and stuff like that and do all the calculus, or you can just study animal behavior and know nothing about math. So both of those are options. Anyway, so they discovered this quantization of the redshift. Okay, the redshift does not follow that nice little formula you would think it would if the universe was expanding, or if things were flying away from us. Okay, one of the reasons I know the scientists can't explain it is because they spent so much time trying to disprove it. And there are two different cases, ladies and gentlemen, where a team of scientists set out to disprove redshift, only to end up amassing a giant mountain of evidence that redshift was a thing. And they were, again, dragged into
the reality that there's redshift, apparently it's a reality, right? So I like to use that as a evidence that something is real. This person did not want there to be redshift, specifically set out to prove that there was no redshift, and ended up concluding that redshift was global, like that you couldn't escape the fact that there was redshift. Look at all this evidence. There's been 2 different cases of that. And even in some cases where an individual galaxy, half of it is closer to us than the other half, and some of the stars in that galaxy have one redshift, and some of them have a different redshift, separated by 1 quanta. How about that? Okay, so this quantization of the redshift seems to be real, okay, and scientists cannot explain it. Okay, I have read, there are 5 or 6 different explanations they have for this, and they're all, it's kind of like their theories on how the moon formed, or their theories about how the Grand Canyon formed. Like, they're so pathetically inadequate to actually explain reality that all the scientists who didn't invent the theory make fun of it, right? So that's how you know that there's really not much to it. There's no, accepted theory for how the moon got here, because you can't. I mean, it's impossible.
In fact, one of the astronomers who was trying to explain the origin of the moon said, look, the best explanation we have for the origin of the moon is that it's observational error. The moon doesn't actually exist. Right. I know. Okay, and they call themselves scientists and us religious. Anyway, so this redshift does exist. All right. It is quantized like this, and we'll come back to this in just a second, because it has to do with Cartwright's idea. It's not my idea. My favorite of the theories is that about distant starlight, that speed of light is actually slowing down. So hold that thought. Redshift is measurable. Okay. Hopefully you study spectroscopy in physical science. The fact that different elements absorb or emit various wavelengths of light, and then you can actually measure that. And so, for example, figure out what the stars are made of, because they emit certain wavelengths of light that you can use a spectroscope to split out and say, oh, there's the calcium line, so this star is big enough to produce calcium. Oh, well, here's the lithium line, so that's a smaller star, it's only producing lithium, right? You get the idea. So redshift is the fact that those lines appearing in a pattern that we recognize, good laboratory science, that they're shifted towards the red end of the spectrum. Red light being lower in energy than blue light, right? Edwin Hubble, of course, discovered the redshift. He thought that it was due to something other than a velocity. We talked about all that stuff. We talked about the fact that you can't get stars. They do not build themselves up through accretion. Accretion just means an accumulation of matter. That's quite impossible. Okay. First of all, you're familiar with the fact that if you drain a very large tub of water, that it will end up spinning really fast in the middle, as opposed to draining something small where it only spins a little bit. So if you're taking a whole bunch of gas and condensing it down into a really small, relatively speaking, volume, your stars should be spinning really, really fast. We don't observe that. Okay. The forces of expansion into the vacuum of space are somewhere between 60 and 100 times the gravitational attraction of these molecules. It is just out of the question to get a star from a cloud of dust and gas. It is so impossible that it's hilarious. Okay. You can't build galaxies either. Good luck.
We'll try.
And of course, the evolutionists have admitted this, right? The silent embarrassment of modern astrophysics is that we do not know how even a single one of these stars managed to form, because, they've already admitted that they are not going to allow God to have that. This whole main sequence and the life cycle of the stars, not a thing, not a thing. We talked about the fact that you cannot get a moon either. It's not just the recession of the moon that's a problem. It's the existence of the moon that is a problem. Okay. Yeah, we'll skip over that for right now. Okay. Problem of distant starlight. All right. There's a lot of Christians out there that sort of, oh, the stars really aren't that far away.
Scientists don't know how far the stars are away from us. You're just displaying your ignorance, okay? Yes, we do, to a very high degree of accuracy. Even if we're off by 10%, they're still billions of light years away. Okay, the universe is huge. We know this for a fact. Yeah, even if we're wrong by a margin of 50%, you still have billions of light years of distance between us and the most distant galaxies. Okay, so yes, we do know the size of the universe to within actually a pretty high degree of accuracy. You can study Cepheid variables if you'd like to get a good idea of why scientists are confident in these measurements. Okay. I will remind everybody that I don't like the idea that God created the light on its way to the Earth, because we can see light from things like the Crab Nebula and other stars that have already exploded, right? So basically, that would mean that God created light from a star that never actually existed, and I'm not okay with that. I don't. That doesn't seem to jive with my understanding of the nature of God. That God is truthful and that He's forthright, and that He's not sneaking around playing tricks on the humans. Okay. It is possible that God created the heavens and the earth, and there was some gap in time between when He starts working on the earth. Okay. So if you're a fan of radioisotopic dating, which I am not, this is the best option for you. I'll remind you that this also puts death and suffering and volcanic eruptions and all this stuff before sin, and so you still have that problem. And again, I don't like that idea. So that's my least favorite. It is also possible that the Earth is in a gravity well. In fact, that's actually quite likely that we're in a gravity well, and that time travels differently for us than it does for the rest of the universe. So I'm okay with that. It's just that if you crunch the numbers on this, you don't get enough of a distortion of time to account for the Earth going through 10,000 years and the rest of the universe going through billions of years. Again, that math is far beyond me. I'm just trusting. When you have young Earth creationists going out there and saying, "Look, this doesn't really work," and they have an incentive for it to work, you can be pretty sure that it doesn't work. That's just my own understanding of it. Maybe we'll figure something out that we didn't know before, and that'll change everything. My favorite is that the speed of light has decayed. Now that's interesting. Again, from Barry Setterfield's own work on the subject, we discovered that the speed of light was measured as decaying up until the 1940s or so. Now, you might say, well, okay, but then they figured out what they were doing wrong, and they measured the speed of light more better, and scientists back in those days didn't know what they were doing. They were kind of primitive and all this stuff. And I'll remind you, that's just a bunch of poppycock, okay? Other things have been measured, like wavelengths, for example, that have been constant this whole time, okay? Scientists hundreds of years ago were able to make very accurate measurements. They were. Started studying the trigonometry that the Babylonians used to do with the hexadecimal system, and you get sort of an idea of the capabilities of humans if they really put their minds to something. If you study the Antikythera device, ever studied the Antikythera device? We might get into that with the archaeology part of our exploration. We'll start next week. Actually, that might be a great way to get into the archaeology segment next week. The Antikythera device is a mechanical calculator that was built approximately 250 years before Christ was born, that calculates the position of all the planets in the cosmos at any time you want to put into your calculator. It even allows for the perturbations in the orbits of the planets, guys, with slotted gears in there. So these guys were able to make very accurate measurements way, way, way back in time. All right.
Back then, how many planets did they actually know?
All the way to Neptune.
Really?
Yeah, Neptune is visible with the all the way to Saturn. Neptune was not known. So you can see Saturn with the unaided eye. Okay. As far as we know, they never had lenses. As far as we know.
Possibly.
Yeah, you would think you'd be able to find those. Lenses They're made of glass. They
You
don't
can find
rust.
one of those
They don't
on
rot.
Is Pluto a planet?
Yes, it's a dwarf planet.
They were like, "Oh, Pluto's not a planet."
Everybody freaked out about that. They should have read the research. All they did was define what a planet was, and Pluto didn't meet that requirement for a major planet.
Why does it matter?
Why does it matter?
Exactly.
We're never gonna get there.
We have better
so-
pictures of the surface of Pluto than we do with the bottom of our own ocean. We don't get any food from Pluto, or electricity, or oil, or,
Yeah, 'cause the
And we
ocean's
never
only-
will.
the
and we
ocean-
never will.
It's like 3% of the
It's a
ocean has
really
been
fancy
water.
rock. Okay, it has a heart on its butt. Like, I get it. It's cute and everything, but seriously, we're obsessed with this nonsense.
So is it like 3% of the ocean has been explored, right?
Roughly 5% of the shallow ocean has been explored. So about, so 8% of the ocean is shallow, and we still have like 3% of that we have not explored.
Do you
Even
think
though
it
it's,
will ever get explored completely?
now at the rate we're doing it, less than 2% of the deep ocean has been explored. And at any given time, there's like 3 humans down there. So,
Why don't
which
we
is pathetic.
Explore that, because there's so much down there.
Yeah, we could.
We
find
discover
life.
new species of animals on every single dive.
Exactly.
It's like whenever.
We just don't. We're obsessed with space travel and building, cities on Mars where the soil is made of perchlorates,
And not.
which is toxic, by the way.
Like, so I was
It's
under
be
water.
in a suit anyway.
I'd rather
That
live
meteorite the
underwater
size of a
than
grain of rice will blow a hole
underwater.
right through your head because there's no atmosphere to speak of.
Where would you rather live, the moon or underwater?
Underwater,
Exactly.
for sure.
The moon has.
There's more stuff down there.
There's a lab, a permanent underwater lab that America runs. Do you guys even know that? Dude, it's 100 foot down. They pressurize it to the same pressure as the ocean. So you live down there and you go diving. You can dive for 12 hours a day and not get the bends. It's pretty legit. Like, seriously, we do not spend, and they're doing advanced studies of like coral growth and all this kind of stuff. It's pretty awesome stuff. Like, why are we, that would be a field trip.
Yeah, can you take?
Where is this at? Like,
How much is it?
Yeah, and also, basically, you could turn any old war submarine into a lab like that pretty easily. Anyway,
How deep
Anyway.
have we gone before?
Huh?
How far is it deepest we've ever gone?
Mariana's Trench.
Yeah, which was like.
The bath escape they used on the Marianas Trench, remember, was experimental. Okay, it had never been tested to those depths before. Jacques Picard, I cannot remember his name. The guy that invented scuba gear. He went down there. Okay, him and another guy. They shared a space approximately the size of a refrigerator. They have one window about that big around with 2 panes of glass. It had to match the exact curvature of the bath escape in order to not make a pressure point, which would crush the glass. When they were about 2 kilometers, is that right? From the bottom, the first pane of glass cracked, shook the whole ship,
We should probably.
and they decided to keep going.
Oh.
This is why women live longer than men. Okay. But seriously, they got down there. They spent 20 minutes at the bottom of the Mariana Trench. We've been back one time. So it's 7 miles basically
Yeah, I
under
haven't
the.
built anything better than that. How long
Which
ago
we
was
Not
very
really.
much so could.
Oh yeah.
Yeah, like
Oh yeah.
that was like what? 30
Rather than sending robots to Mars to
Let's
find
send
really
robots
fancy
down.
rocks.
You send robots down.
The Meg's got my eyes.
No. Anyway, so I want to point out that 17 different times the same equipment was used by the same scientists to measure the speed of light and gave a lower result. Scientists at the time complained that if the speed of light was a constant, how was it that invariably new measurements gave lower results than previous measurements? Okay, they have ways of knowing how accurate their measurements are. If you've taken chemistry, you know about significant figures, being aware of the limitations of your equipment, right? This is very straightforward in science. One of the things we're obsessed with is knowing whether our equipment is actually accurate or not. Okay, so the speed of light was measured as decaying. In that time period, the speed of light from the 1600s when it was first measured lost about 2% of its total speed. Okay,
So,
In the 1940s, it was decided that they would stop doing this research into the speed of light because they didn't like where it was going. Because some things they measured as constant, like wavelengths and things like that. Other things they measured were not constant, like Planck's constant. Planck's constant is not constant. It seems to always be increasing. And somebody figured out, now this is one of the dangers of being a specialist. The chemists were measuring Planck's constant. The astrophysics guys were measuring the speed of light. And it was a long time before somebody figured out if you multiply the speed of light by Planck's constant in any time in history, you get a constant. So Planck's constant is increasing at the same rate that the speed of light is decreasing.
so
How is it possible that the speed of light is related to the resting mass of an electron? They are, though. And I'll show you why. Okay. So, by the way, in the 1960s, we all switched over to the atomic clock, which gives the exact same value for the speed of light no matter what. Okay. Unfortunately,
we've learned about atomic clock. I've learned about atomic clocks before. But what exactly is an atomic clock? I forget.
they're using the vibrations of an atom to measure
That's what, yeah.
the
We
passage of
have
time.
many of them.
We have quite a few.
Quite a few.
The whole point is to make a super accurate clock that never loses time. So an atomic clock was made that would lose about 1 second every 2 million years. Extraordinarily accurate. And when they built the thing, they figured out that it did not agree with dynamical time. So we can actually figure out exactly how long it takes us to get all the way around the sun, because we can measure the angles to the stars and all that. It turns out that atomic time runs differently than dynamic time does, okay? And that it is possibly still changing slightly, right? This also has to do, by the way, with the decay of radioactive isotopes. Radioactive isotopes, if they take a long time to decay now, possibly it's because of the same phenomenon that's causing the speed of light to slow down and atomic clocks to disagree with how long it takes us to get all the way
So
around.
do the atomic
the sun.
clocks deal with the daylight savings time, stuff like that?
Oh yeah, that's arbitrary. Everyone just decides it's a different time and they set their clocks, differently. But atomic clocks, what we mean is that you should be able to design one that, like a grandfather clock, if you wind up the spring and all that and you compare it with the time on your phone over a couple of months, it will actually disagree.
It's slower.
It's slower, it's faster because of the
Slowly.
springs or because of the weights.
It's not perfect.
It's not a perfect clock, right? Quartz clock, same thing. If you have a quartz watch, every couple of years, it'll, if you synchronize a quartz watch with, let's say, a grandfather clock, they'll disagree with each other. They'll drift, okay? Atomic clocks are not supposed to do that.
Well,
So they don't change when the time change happens?
No, again, with time change, with daylight savings time, we're just like, okay, everybody, spring forward. We're all like, click, and we set our clocks forward.
The thing I think is stupid is that
It's dumb.
it's like daylight savings, it goes forward.
it's just like they want to screw their lives.
I think we should have a fall back and move all the clocks back 1 hour every Sunday.
Okay.
You know what I'm saying? Yeah.
That would be a very weird.
If we're gonna have daylight savings time and spring forward, let it happen at 3 o'clock on a Friday. Yeah, that's all I'm saying here, guys. Okay, so important to note that these things seem to be related. Increase of Planck's constant, which has been measured as increasing the resting mass of an electron, the decreasing speed of light, and the quantization of redshift. This might all be due to a field called the ZPE. Okay, which I think we talked about before. Have we talked about? Okay, so ZPE stands for zero point energy field. Okay, hypothetically, this is the reason why electrons do not crash into protons and turn everything into neutrons. Okay, so why? So the question arises: why don't they? You got your standard model of the atom, and you might say, wait a minute, Kurt, right? That electron is attracted to the proton. It is. All right, so why doesn't it just smash into the proton and become a neutron? That's what neutrons are. Neutrons, if they're all by themselves, actually decay into a proton and an electron. Is that nuts? Why do they do that? You would think a neutron would be way more stable, right? And you'd be wrong. And the only reason why you'd be wrong is if they're constantly absorbing energy from something, an energy field perhaps, that we call the 0-point energy field. Now, we're not sure that this actually exists, but if it does, it would constantly be adding energy to the electrons. Now, the crazy thing is, if you do the numbers on this and you figure out how much energy there has to be in the 0-point energy field, you could take an amount of space like that and run the United States for like 1 million years off that energy. It's a lot of energy, which has caused astrophysicists to describe it as the seething vacuum. Like, where did all this energy come from? This is really freaking us out. So a lot of scientists don't like it for that reason. It's just uncomfortably huge. Okay.
Don't touch it.
So where did the 0-point energy field come from? Well, good question. Barry Setterfield has an idea, which I think is brilliant, and that is based off of the scriptures. God describes himself as having stretched out the heavens 17 times in the Bible. Okay, it's always past tense. Like God stretched out the heavens, now he's done. Okay, so apparently this was done during creation of the heavens. Okay, and Barry Setterfield, of course, Einstein described space-time as a fabric, right? So God says he stretched out the heavens like a tent. Interesting. So maybe it's an elastic, has an elastic nature to it, and stretching it out imbues space-time with energy. Maybe that's where the 0-point energy field comes from, and that is what allows matter to exist. Okay. So if that happened, if God stretched out the heavens like a tent in the past, then he would have created the 0-point energy field. Now, the crazy thing is, he would have also created a lot of matter, okay, because matter and energy are interchangeable. See, E equals mc squared. You can actually convert between mass and energy. So you would have created so much energy in the universe that you also create these little virtual particles. And I don't understand the math behind that, but apparently way smarter people than me agree that that's what would have happened, okay? So in other words, the density of space is increasing over time. Now, it increased really fast at the beginning of the cosmos, and it's sort of petered off now. The rate of increase of the if you want to call it the density of space, is decreasing now to the point that the speed of light hasn't been affected all that much in recent times, okay? But interestingly, the speed of light would have been blisteringly, almost instantaneous, thousands and thousands of years ago, and only decayed to its present rate more recently. This also means the 0-point energy field would be changing. The 0-point energy field actually would have changed over time. That, according to Barry Setterfield, is what caused redshift to be quantized. You see, all these energy fields are separated by, that's why we call it the quantization, separated by one quanta of energy. What is a quanta of energy? That is the distance between two orbitals of electrons in an atom. And you're familiar with the fact that higher energy electrons emit different wavelengths of light than lower ones. That is spectroscopy, right? That's why we can identify various elements by the photons that they spit at us, okay? So basically what we're saying is that if you look back through the cosmos at objects where the light has traveled a long time to get to us, that light was emitted during a time in the universe when the 0-point energy field was weaker, and therefore the light was lower in energy and therefore redder. And as you look through the cosmos closer and closer to the Earth, you're getting closer and closer to the present day 0-point energy field, which is emitting bluer light. Okay. So this idea that the speed of light has decreased from some insane value near the creation of the universe fits with a lot of different phenomena, similar to hydroplate theory. We can explain lots of different stuff. So scientists like that, okay? The problem with it, of course, for the evolutionist is it works on a time scale of 6,000 to 10,000 years, right? And so again, you can use the present, the measured decay in the speed of light, about 2% over the last 250, 300 years, and look back in time and say, okay, so 6,000 to 10,000 years ago, you'd had a pretty dadgum fast speed of light. Oh no, by the way, we'd also have a very fast decay of radioactive isotopes, which again, we've discussed with polonium halos and things like that, that the radioactive decay seems to have been a lot faster in the past, helium being stuck in the zircon crystals and things like that, than it is in the present, okay? So you get, they're all kind of children of the same parent. This also increases, because there's more energy available, this would increase Planck's constant, right? Because again, you can convert that into mass. So the resting mass of an electron is increasing over time, okay? So this is my personal favorite idea for the observed distances we see in the universe, that the speed of light has decayed from some extremely high number. And again, we have very good evidence of this happening. Atomic clocks seem to be slowing down. And so atomic processes are operating at a slower speed today than they have in ancient times. And perhaps the density of space-time itself has changed as the zero-point energy field has also changed. All right. Oh, Barry Satterfield, if you're curious about getting into the actual math on all of this stuff, he has 5 anomalies that he explains with this whole theory: the quantization of the redshift, the speed of light, which was measured as decreasing, the increase in Planck's constant, the increase in the mass, the resting mass of an electron, and the slowing of atomic clocks, rather, in relation to orbital or dynamical time. All of these things are controversial, okay? However, the evidence to me seems to be overwhelming. If you just look at the evidence and you say, okay, you know, what are the chances that the speed of light is constant and yet it was measured as decreasing 17 times in a row? Well, you can actually do a statistical analysis on that and say, okay, well, basically we can be 98.5% certain that the speed of light has actually been decayed while we've been measuring it, okay? And oh yeah, if you use atomic clocks to measure the speed of light, you always get the same value. So keep that in mind. And there's also a research paper that Satterfield put out on the topic, which has been published. Although when the scientists realized the implications of it, then they were not interested in hearing from Barry Satterfield. So Tift in 1976 discovered the quantization of the redshift. All right. Yeah, scientists are trying to dispute it and refute it. And most scientists are, oh, well, all we need is more data. So Martin Crossdale reported a finding of a quantization of the redshifts using different samples of galaxies in increments of that, whatever that means. In 1990, Bruce Guthrie and William Napier reported finding a possible periodicity in the same magnitude for a slightly larger data set, limited to bright spiral galaxies, excluding other types. These guys actually set out to disprove quantization of the redshift. 92, the same dudes proposed the observation of different periodicity in increments in a sample of 89 galaxies. 92, those guys reanalyzed the redshift data from a very large sample and concluding there was unexpected periodicity of redshifts. 94, those folks reanalyzed redshift equations and concluded that there was unexplained periodicity of, you understand where we're going with this. A lot of these scientists are just kind of coming along going, wait a minute. 97, some of the same scientists, again, who have set out to disprove this. So far, the redshifts of over 250 galaxies with high precision HI profiles. I don't know what that means. have been used in the study. Consequently, selected subsamples of the data sets of sufficient precision examined so far. The redshift distribution has been found to be strongly quantized in the galactocentric frame of reference. So the formal confidence levels associated with these are extremely high. Yeah, so apparently quantization of redshift is a thing. 2006, one of these studies actually denied quantization of the redshift. Somebody else analyzed the data and said, wait a minute, you forgot to include the motion of the sun through the cosmos, because that creates a real Doppler effect. You have to take that into account. So somebody did a math boo-boo and tried to deny quantization, and basically they've been disproven. As far as I can tell, again, light speed has been measured as decaying. Many different methods are used to determine the speed of light. I want to say 40 different experiments were done to determine the speed of light. They all arrived at the same conclusion, except that it kept decreasing over time. 17 cases where the same equipment was used by the same scientist at a later date gave a lower result. Okay, and Debray published in 1941. Again, they were getting really annoyed at all of this because they were determined to prove that there was no God and that the universe didn't ever change. Okay, so he says, okay, well, if the velocity of light is constant, how is it that invariably new determinations give values lower than the last ones obtained? There are 22 coincidences in favor of a decrease in the velocity of light and not a single one against it. That was published in Nature, and the emphasis is in the original. So the scientist is emphasizing that. Keep that in mind. Sometimes you see quotes and they will emphasize words that the person who wrote it or said it did not actually emphasize. So watch out for that. Emphasis is in the original. Okay. Planck's constant apparently is increasing with time. Even more strangely, it always gives a constant if you multiply it by the speed of light. Well, Planck's constant is possibly, we think, a measurement of the zero-point energy field. Keeps electrons from crashing into protons. Maybe. It is a way to measure electromagnetic radiation as a function of time and energy. And atomic clocks do not run at a constant rate. Number of atomic seconds per year is becoming fewer. And if this is tracked back thousands of years in an orbital year, it is many times longer than the current atomic year. Radioactive decay would have been much faster in the past, much faster in the past. And using atomic clocks to measure the speed of light is kind of like using a ruler to measure a tape measure. If your inches are shrinking, then you'll have the same number of feet in a tape measure, right?
How larger atomic?
Pretty good size. The material they use is really rather small, but the equipment actually to measure the vibrations and keep track of all that, that's fairly large. Like the size of this room.
Contain a vibrating data.
Very, very carefully, I assume. And again, we have historical evidence for this
So,
in helium trapped in zircons.
so can atomic clocks be good and like
No. So you're, first of all, I don't think they actually use radioactive elements. If they use rubidium or cesium or something like that,
atomic is
strontium. Yeah, everyone's like, "Oh my gosh, atomic!" You know, kind of like electromagnetic radiation. If you say electromagnetic radiation, people freak out. You know, like, what's coming through the window right now? That's what light is, right? So yeah, most of the electromagnetic radiation you come into contact with is perfectly harmless. UV, yeah, that's a little dangerous, especially if you have pale skin such as myself. You need to protect yourself from that kind of stuff.
I can take it.
Malignant melanoma is not a good way to go. So just keep that in mind. Atomic masses have increased over time. So the resting phase mass of an electron has increased with each measurement taken. And again, other things that we measured as constant were constant over time, like wavelengths. So perhaps this is due to God having stretched out the heavens. Okay. And this is the explanation of it that's maybe a little bit more better than the one I tried to give earlier. So he assumes that stretching in space-time in this manner would infuse it with incredible amounts of energy. So much energy it actually create Planck particles, which appear in positive negative pairs. And as the stretching continues, you create more of these, okay? And they get separated over some distance. And as they come back together, they annihilate each other and increase the energy of zero-point energy field, which increases the density of space-time, decreases the speed of light, and increases the amount of energy available to an electron as it's orbiting an atom, and thus bumping it up over time as it can absorb all this energy, and finally it gets enough, it jumps up one quanta, right? You get vertical particles to form, increase the density of space, allow the speed of light to decay over time. Keep in mind that the speed of light decreases as the density of its medium increases. So light travels slower through glass as it does through the atmosphere, which is the only reason I can actually see your faces right now, because, you know, refraction and all that, okay? Like, bless you, poor kid's allergic to refraction. So diamond, for example, speed of light through diamond is 2.5 times slower than it is through the air, which is why we say gems have a fire to them. They don't really. They just seem to, wow, it's taking light from over here and refracting it. Into your eyeball. Okay. You can also make lasers out of them. So radioactive decay decreases over time, as well as increasing mass of atomic particles over time. Energy builds up. Eventually, it allows electrons to make a quantum jump. And at that higher energy level, they emit bluer light. So we expect redshift to be quantized. And light that was emitted thousands of years ago would be redder than light emitted more recently. So, do we know what's going on here? No, we have a pretty cool theory, I think. Okay. And again, I'm going to harp on the idea that I don't think that God created light on its way to us. Okay, supernovas sometimes mean that galaxies or the stars actually never existed in the first place. Galaxies appear very close to the same age, no matter where they are in the universe. And so the last part of this class today will be a little tour of the universe. Okay. The pictures of the universe, right? So unfortunately, a lot of these sort of incredible unlikelihoods result in people claiming that there's a multiverse, and in other philosophies called panspermia, and yeah, we're not going to make jokes about that. The multiverse idea is, to me, a Hail Mary desperate attempt to try and shoehorn a way to escape the incredible unlikelihood of living things being in our universe, right? And they're admitting that their philosophy is not scientific, right? The multiverse cannot be, by definition, cannot be scientifically proven, right? So what they're saying is, well, and we know that these universes wear out over time. If they're like ours, entropy wears them out over time, so you have to replace them. Well, how are you getting all these universes popping out of existence? Like basically, you have to believe in a giant universe creating machine out there, spitting out all these universes all the time to replace all the ones that are, you know,
God.
defunct. Yeah, it's your God. Okay, well, now we're back to polytheism, where everything's God. You see what I'm saying? You can't get away from this whole idea. All right. So the question is not, does God exist? The question is, who is God? Maybe we should figure out what he wants. Maybe he's powerful enough that we should figure out what this guy's all about. We talked about the fact that matter and energy cannot be destroyed, so the Big Bang would violate the laws of physics. Second law of thermodynamics says entropy increases in any system, so your bedroom constantly becomes less organized. Your garage constantly becomes less organized over time. And adding energy to it doesn't help. Dynamite is not going to solve your problem. It will not make a nice, maybe it doesn't mind travel, but yeah, you have to physically organize it. It takes information to create information, to bring order out of chaos, right? I think we're done.
Puts back together.
entire garage and lost it.
Sir Fred Hoyle, remember the steady state guy? Sir Fred Hoyle, he has been quoted as saying a common sense interpretation of the facts suggests that a super intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. So for example, the Fibonacci spiral describes a spiral galaxy, the arm bands of a hurricane, the shell of a nautilus, and the unfolding of a fiddlehead's fern, and also very much lots of other phenomena follow the same formula. What are the chances? What are the chances the galaxies and ferns follow the same mathematical formula? I don't care where you look, you're going to find the fingerprints of God. Okay, as promised, I'm going to take a little tour through the universe here, right quick. If I can find I think most people have really no idea of how big the universe is. Okay, so the Hubble Deep Field comes from the fact, it comes from the fact that the Hubble Space Telescope has a whole bunch of teams of astronomers that get to use it every once in a while, and they get to point it at a particular spot they want to study. There's 2 weeks of the year that they just turn the scientists loose and they get to do whatever they want. They pointed it at the darkest spot in the sky for the entire 2 weeks. So they're taking a picture where the shutter speed is 2 weeks. So they're allowing enormous amounts of light to be captured over that period of time, okay? And they created the Hubble Deep Field. Now,
Are these galaxies or is this
now
one
important to realize that when you're looking at an astronomical image like this, stars always look like points of light, no matter how many times you magnify them. So everything that is not a point of light is a galaxy. So in this particular image, I see one star.
What about that thing?
This guy is a galaxy. Galaxy,
No,
galaxy,
no, no,
galaxy,
no.
galaxy, 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 galaxy,
Okay.
galaxy, 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 galaxy. You understand what we're saying here?
You know, galaxy.
I want to see some sort of.
Well, it's surface. I mean, it's swirly, so I'm thinking like Milky Way or a galaxy.
Some galaxies are spiral. You see one here. There's a nice spiral galaxy. Okay. There's a point of light. Okay, that's a star.
There looks like there's a star under.
There's a nice spiral galaxy. This particular spiral galaxy is probably somewhere around 100,000 light years across. Probably contains something like 100 billion stars.
That's it.
This one right here, yeah. It doesn't even have a name.
So does that mean
It has
that
a number.
that star that we just went above it is the size?
No. It's way closer to us.
Okay, it's just closer. to us.
Yeah.
Yeah, this is too much.
So once you get so far away, you can't see light from individual stars anymore.
So it's
Only
putting
galaxies
those-
are visible.
So it's just putting it on a 2D picture, so things that are.
Right. So you're taking a picture of this entire region of space. So it just so happens there are some stars in that picture that are close enough for you to see them. And then as you get further and further away, you can't even see individual stars. All you can see is the combined light of hundreds of billions of stars put together, which is most of these galaxies probably contain somewhere in the neighborhood of 100 billion stars. And again, I want to point out, we got a star here, we got a star there, we got a star here, and everything else that you can see.
To the left, like in a clump of.
This one? This one?
No, down, like in the right. And up, like.
Oh, I see it.
Is that
That little red thing?
That a red thing?
Down, right there.
No, that's a galaxy.
Yeah. You didn't know.
Oh, this red thing.
Come on.
I don't think my magnifier is working very well. Yeah, so some of these little spots here are galaxies. They're just so far away you can't even see the structure of them.
The red
Just
galaxies.
different
Older galaxies.
yeah. The crazy thing, or they might be nebula. So a lot of galaxies still have nebula around them, which is an indication that they actually haven't been there that long.
How much of an IQ do you have to pass this part? I mean, if it's like
Probably
100.
100 is average in America. Not average the rest of the world. Huh? No.
IQ tests are, no, IQ tests are very.
Questionable.
I've
Very
taken an IQ
questionable.
test before, and I didn't finish it because I thought it was dumb.